Okay, so I just quoted directly from Wikipedia here, which I don't think I've ever done in my physics notes before. That work, it was a good quote. Work is the energy transferred to or from an object via the application of force along a displacement. So I kind of like this because it just says work is the energy. Work and energy are interchangeable essentially. You can do work and put energy into something. You can use energy to do work. The units are the same. The units are joules. Grab a new handout. They're on Madeline's desk, and you can move them, Madeline, if you want to put them somewhere else. Um, have we talked about why sometimes the units are capitals and sometimes lowercase? Why, Alex? Do you know? It might be in chemistry. Like somebody pointed out molarity, which is a capital M, right? But that doesn't follow the convention in physics. Do you know what it is, Darren? Yeah. So, right. In physics, is generally if it's named after a person, it's capital. So joules are named after James Prescott Joule, and newtons are clearly named after Newton. Grams were named after anybody, so that's a lowercase. But that's generally the rule in physics. If you ever run across anything that doesn't obey that rule in this class, let me know, because I think it applies to all the units that we use. Big G, ooh, the gravitational constant. Yeah, but that's not a unit. Okay. Yeah, tell me if you can think of any other units. All right. Oh, I didn't really read I didn't emphasize the important part. So work is the energy transferred to or from an object via the application of force along a displacement. So that's going to be important, this along a displacement part later on. It's going to play an important role in some specific situations, but generally it's just an application of a force. Energy is the ability to do work. There are two kinds of energy that we've talked about already. There's kinetic energy, which is energy something has because it's in motion. And then there's potential energy, which is stored energy. And you can have all kinds of stored energy. You can actually have, in a broader sense, different kinds of kinetic energy. So if I have a ball rolling down a hill, it can actually sort of have three types. We're only going to focus on one right now. So the ball is moving this way, right? So it's kinetic energy we're going to do based on that movement. But what else is the ball doing? How else is it moving? It's going parallel to the hill, but it's also rotating. So when we get into rotational motion, we'll focus on what we call translational kinetic energy. That's what we're doing now, and rotational kinetic energy. So that what you would see if you put a wall here, and we're a frictionless wall, and maybe you had this is ice, the ball hits the end, it stops moving downhill, but it's going to keep spinning for a while because it still has that rotational kinetic energy. And also, if you zoom way in on everything to the molecular level, what are the particles inside here doing? They're moving around. I mean, if it's a solid, they're just vibrating back and forth. If it's a liquid, they're actually moving, but there's no net movement. So there's sort of kinetic energy. There's kinetic energy from this whole ball going down the hill. There's kinetic energy from rotating. And then there's kinetic energy of its molecules, which we really call thermal energy instead. So energy of motion can be a lot of things, but in the beginning, we're just going to say something's moving right to left. That however fast it's going that way is determining its kinetic energy. And then for potential energy, there are just two kinds of potential energy we're going to be dealing with. We'll store energy in springs, and we'll store energy by lifting things up. So gravitational energy and spring energy. All right, examples. So this is saying, by the way, big picture of this, what we used to do, I changed the notes around this year. We used to start out with the formula for work. And then we would go to the formula for, where is it? It's way back in here now. The formula for power. And then we would go over the work energy theorem. And then a few other things, and we would practice all these little bits and then put it all together in the end. And I'm thinking that it's better to make sense of it all in the beginning, and then it'll be better. The bad thing is we're not going to really be able to do anything until we get to maybe the 7th page of these notes. So we've got some notes today and maybe half of tomorrow to get through. All right. We need an example of work being converted to kinetic energy. Work is applying a force over a distance. Kinetic energy is energy of motion. Anybody think of a situation where you do work on something and you give it kinetic energy? Push what? Push a hockey puck. Yeah, that'd be great. So you put, like, I'm going to say a motionless hockey puck gets pushed. If there were more space and more time, I might draw a picture and really focus on this. But the push, that's the force times distance. That's what work is. So if you're pushing it, you're doing work on it, and then it has motion, and that's the kinetic energy that it has. All right, so the opposite of that would be kinetic energy is converted to work. So can you think of a situation where something has kinetic energy and some of that kinetic energy gets turned into work? Brexton? You could do that. I might not write that one because that's kind of complicated, but yeah. So somebody last class said, you catch a ball. So if this is my finger and the puck is coming at me, it's got kinetic energy. What happens when it hits my finger and my finger tries to stop it? My finger gets pushed back a little bit. And in the process, this comes to a stop. So this was moving fast, and when it hits my finger, it's going to slow down and do work on my finger. I'm going to use a slightly different example, but that one's good. I'm going to say, and I don't know why I got stuck on this. This one's actually hard to come up with the perfect example. A moving car pushes over a fire hydrant. I don't know why. You can write whatever you want to. So a moving car, that has kinetic energy, and a fire hydrant could be a fire hydrant in motion, but probably not. It's probably a stationary fire hydrant. But when the car hits it, the car is going to apply a force, and it's probably going to push it over a distance, unless it's a really, really massive fire hydrant. If it's pushing it over, the key here is this force has to be applied over a distance. If there's no distance, just a force, you don't technically get work in physics. And I'm just going to add this in to clarify things. Slowing down in the process. The reason I want to write that is because I want to make it clear that the car was moving, it had some kinetic energy, but after this it's less kinetic energy because it used that energy to apply this force to the fire hydrant over some distance. Keith? Yeah. A domino? So if you have a domino like this and another domino here and you push this domino over, yeah, so when this one when this one's moving, and it hits that one, yeah, then it would push it. Yeah. Apply force. Okay, so work converted to potential energy. Two kinds of potential energy. You can have spring potential energy, you can have gravitational potential energy. We could choose either for an example. Does anybody? What's that? Pick something up. I'll just write that. Pick something up. So this one almost needs a little bit of further explanation, but if it's right here, it has low potential energy, but when it's up here, it has high potential energy. And in order to get it there, what do you have to do? You've got to apply force. Force equal to what? Greater than or equal to what? Like if we saw, it would be that, but you could also calculate it by using what's the force that it would take me to lift my mouse? What? Yeah, it'd be the weight of the mouse. So if this is the object, and we just drew a picture of the object sitting here, there's the normal force, and there's the weight. And right now they're balanced, if that's my mouse. But if I want to lift it up, I have to apply a normal force that's greater than that weight, or at least equal to it. Greater than it to get it moving, but then equal to it to keep going. So anyway, to lift something from there to there, you have to apply a force that's pretty much the weight of the thing over whatever that distance is. And if the distance is bigger, you're going to apply that weight for a bigger distance. You're going to get more work. You're going to put more potential energy into it. All right, potential energy converted to work. So this was work converted to potential energy. How do you turn potential energy into work? Or what's that? Drop something. Drop something. And I'm going to add some clarification. So the work in this case, what's applying the force when you drop something? Gravity. So the work from here, that's the force of gravity. And then times whatever the distance is that it's falling. That would equal the work that's being applied here. And the potential energy is just, whatever energy it had because it was up high in the first place. And the beauty of all this is going to make problem solving a lot simpler, because if you can calculate how much potential energy this thing had, then you'll be able to say, oh, well, that equals the work done on it as it falls, or the work it does as it falls, and vice versa. Yeah?
Force is a capital.
Force what?
Force is a capital variable.
But not a unit.
Oh,
Yeah. Keep trying. Yeah. For variables, we use capitals and lowercase, just kind of, I don't know. I don't think there's a rule there, but I don't know. All right. Work can be calculated with force times distance, but it's really important that it's the force in the direction of movement. Oh, this camera is so much better. This is the other camera. So here's an easy question, or easy problem. Child pulls a wagon to the right for 4 meters. So here's the pull. It says there's a 10 Newton force. The distance that it travels equals 4 meters. How much work is done? 40 joules. Work is force times distance. Work is 10 newtons multiplied by 4 meters, and that equals 40, and the unit is joules. And when you do that, what's going to happen to the kinetic energy of the cart? It increases by how much? 40 joules. Unless there's friction or something else robbing energy from the system. So this would be it's this example right here. It's like the motionless wagon that gets pulled instead of the motionless hockey puck. All right, here's the military cadet. I couldn't find. They might look like that. A 60-kilogram military cadet holds a plank for 10 seconds, and I'll just tell you that the weight of a 60-kilogram military cadet is 588 newtons. You don't have to, that's not really the point here to calculate weight, but you kind of need that. I could have said a 588 Newton military cadet. Right.
So we use the same.
Ah, yeah, so no, it is. So work, what I'm going to try to do is, yeah, you can't even, it looks the same, doesn't it?
Yeah.
I should strive harder to make this look like a capital pointy W. I'll start trying to do that now. And this one to look like sort of a butt. Saggy butt. There we go. Or whatever you want to. Let me just call it a small rounded W. This is a large pointy W, and I'll use a small rounded W. And it's going to get worse when we get into angular momentum and we have omegas, because a lowercase omega looks exactly like this. Yeah. So that's weight. Maybe I shouldn't even use W. Maybe I should have just said mg because that would have been better. Let's. All right. So before I do the calculations, how much work does this person do? Using the strict physics definition of work. Work to, if you weigh that much, to hold a plank for 10 seconds. Yeah, Cam? 0. Yes, work is force times distance, and the force, like, supported by the hands and the feet together, is going to be 588 newtons. But what's the distance? 0. So 0 joules. And this is where the answers we get in physics problems aren't really going to jibe with real life sometimes, because this is definitely taking energy. She's using energy to do this. And as her energy diminishes, that energy needs to go into something else. But in terms of like this definition of work, there's no work done.
I think the issue is not taking into consideration that, like, if it's the same situation, it would be defined in the same way if the person was just laying on the ground.
Yeah, that's true. Right. But this would make you tired, and being on the ground wouldn't. So it's more complicated. All right. And here's another more complicated, kind of different situation. Another wagon. And the wagon's being pulled, but it's being pulled at a 30-degree angle. And the force, the tension in the rope is 20 newtons. And the wagon is being pulled for a distance of 6 meters. Now, if you're going to pull this wagon and move it 6 meters and do it, bless you, do it as efficiently with as like small energy expenditure as possible, would you pull at this angle? What angle would you use? Like this one, because the lifting part is really wasted energy. You're not accomplishing much, but maybe it's just ergonomically easier to pull at this angle. So what we're going to have to do is resolve this. So we can resolve it into the x component of tension and the y component of tension, and which one of those is actually going to be doing the work that we'll calculate, x. Because this formula means the force that's in the direction of displacement. So that's what the F should be. So let me do Tx. How would I get Tx? Cosine or sine? Cosine of 30 times 20. And it comes out to 17.3. Right, 17.3 newtons for that. And then the work is 17.3 newtons times 6 meters, which is, I got 104, but, okay. All right, 104, call it. 104 watts? Joules. And there I go again, doing rounded ones. I think you can tell by context what's what. We won't actually deal with weight much in this unit. That's the nice thing. So, okay. Mechanical energy, thermal energy. Mechanical energy, that's what we're going to be focusing on for this unit. They're determined by an object's motion or position. Examples we'll work with are kinetic energy, just like this thing's moving to the right, so it has kinetic energy. We'll be able to calculate it. Gravitational potential energy, it's high or it's low. That's what's going to determine gravitational potential energy. Spring potential energy, the spring is compressed or stretched. That's what's going to determine that. Those are all mechanical. Thermal relates to temperature, and temperature is what I was talking about here with the random motions of the molecules inside there. We'll point to this as maybe where the energy is going sometimes, but we'll never be calculating anything with thermal energy. All the formulas where we calculate something are just going to be mechanical. Law of conservation of energy. So here's the simple law of conservation of energy, which I think is pretty simple to understand. It's just this equals this. So what I've tried to do here is list all the kinds of energy and all the kinds of energy, or at least mechanical energy, and say that the total energy before equals total energy after. Conserved means that the total doesn't change. So here, let's do a diagram, kind of a graphic portrayal of this. Somebody's on a skateboard. There's no friction. There's no air resistance. This is a perfect physics world. They're going fast at position 0. They're going slower, and then they stop at position 2. And what would happen next? They go back down. So here we've got kinetic energy that's turning into what? Potential energy, and then potential energy turning into kinetic. And there's work being done kind of to make that happen, but we're not focusing on that right now. All right, so let me just start it out by, this is the kind of thing I'm imagining here. That's the kinetic energy of the person right there. How much potential energy should we give them? Yeah, this is arbitrary. You get to choose. You get to say this is 0 if you want, and I would choose 0. But if this were a more complicated thing where this is actually the lowest point, you wanted to call this 0, then you'd give them a little bit. We could do that, but let's not. Let's just say they're at the bottom here, so the potential energy is 0. All right. Total energy would be this plus this, so it's just a little bar as tall as kinetic energy. What do we do now? Just go ahead and sketch it if you want, or at least imagine what you would do here. All right, kinetic energy, how does it compare to the original? It's less. We could make it half. We could make it a quarter. I don't know exactly, but I'll make it a half. Actually, for the fun of it, if I wanted to go a little more than half or a little less, what do you think it might be? No, I think I don't know. I think it's half. All right, I'm going to do half. I kind of want to make it more than half, because then when I did the potential energy, what would I do? It would be a little less than half, because the potential energy and the kinetic energy need to add up to what? Yes. So the height of this needs to always be the same, because energy is being conserved. So the total can't change. So whatever amount this goes down by, this needs to go up by the same amount. Okay. So the last picture, how much kinetic energy is here? 0 plus as much as that was. So basically all the kinetic energy they had in the beginning has now turned into potential energy. And then it's going to go back. It's going to reverse itself if there's no friction. So this is a simple world where there's no friction. And some of the problems we do will be no air resistance, no friction, but then some will be more complicated. Now we get into the more complicated stuff. So that's just for very specific systems where the total amount of energy remains constant, mechanical energy. But in these systems, or in the broader sense, the total amount of energy is represented by this. So if you take kinetic energy plus potential energy plus other energy, that should always equal kinetic energy plus potential energy plus other energy in the end. So total energy in the beginning equals total energy in the end. It's always true for a closed system. This isn't always true because you have friction and stuff, and we're just focused on mechanical energy. But this one, for a closed system, meaning nothing being acted on from the outside, this is the big picture, more complicated picture. So this is one way to look at it. And it says other energy can be chemical, it can be electrostatic, it can be thermal, it can be nuclear. Anything that's not a spring being squeezed, or something being raised or lowered, or something moving left or right, would be the other energy. So this is what we did yesterday. This is kind of the tidy thing I was trying to get you to derive. If you look at the mechanical energy in a system before some event and the mechanical energy in the system after an event, the way that gets changed is by work. So you can have some positive work done and you can add energy, so you have more energy afterward. Or you can have negative work done and you can take energy away. And what kind of work do you think friction usually does to a system where things are sliding around? Does it add energy or take energy away? It takes it away. Now, you can use energy to run and things like that, but when things are sliding, it's going to take energy away. And that energy, if we use this, gets turned into what kind of energy? So it gets turned into thermal energy through heat. All right. Here, this, and hopefully everything will start coming together with these two examples. And the other class, all we did was we got through this page and that was it. So this is going to be an example of negative work by non-conservative force. I didn't really I need to go back and explain this non-conservative force thing because it's a weird sounding word. So a non-conservative force is something that causes energy to not be conserved. So if you have the skateboarder going up the hill, energy is being conserved here. We have the same amount of energy. But if there were friction, by the time we get to the end, what would happen to the total energy? It'd be smaller. Or if somebody was pushing the skateboarder, then it would be bigger. So this WNC is work that gets done that causes this total and this total not to be the same. So it's just preventing energy conservation from happening. Okay, to a particular system. So here we have a box. It's sliding down a hill, and it's a very special hill because there's just enough friction so that by the time the box gets to the top of the bottom, it's stopped. So it's going slower and slower. You would have to tilt your hill just right and start the box at just the right speed to make this happen. So the first thing to do is to do kind of what we did before, except we've got a different equation here. This is the equation from yesterday. And I'm zooming out, zooming out, zooming out. So this box is focusing on this transition. This is the left part. This is this part right here. So if I look at the box at the top, kinetic energy, potential energy, we'll come back to this afterward. Do we? Ah! Very disappointed. Oh well. Bye. I always think I haven't